All right, let's look specifically at definitions of conservative and non-conservative forces next. And then I've got a couple more examples for you, and then I'll set you loose on some independent problem solving. All right, so conservative forces are forces, right, primarily like gravity. Here, I'll write that at the end. Forces that allow mechanical energy to be conserved. Right, the total energy is never reduced, but conservative forces don't reduce the amount of mechanical energy. So this is an example of this is gravity. Okay, when gravity is a force that's doing work on an object, that work just changes the mechanical energy from kinetic to potential back and forth. Okay, non-conservative forces, they oppose motion and reduce the amount of the total energy that is available as mechanical energy. Okay, they oppose motion and reduce the amount of total energy that's available for mechanical energy. Work done by non-conservative forces. Turns to thermal energy. Okay, and examples of forces that are non-conservative are friction or air resistance. Okay, non-conservative forces are typically called resistive forces. So we could say force non-conservative. We could say force acting by resistive forces. And then the work done by non-conservative forces, just like in that equation we wrote W and C. And we know work equals force times distance. So work done by non-conservative forces is equal to the resistive forces times the distance over which those resistive forces are acting. Okay. All right, let's try another example. So here we've got a skater who drops into a half pipe with a speed of 5.4 meters per second. We're neglecting friction and air resistance. What is the height above the ramp H that this skater will be able to reach? Okay, so this isn't a like friction or air resistance non-conservative forces one, because we're neglecting friction and air resistance here, but it is an example of a non-traditional reference level, excuse me, I'm with hiccups. All right, so what we know is that the skater drops into the half pipe with a speed of 5.4 meters per second. So let's call this position 1. Right here at position 1, we've got a speed. Speed at position 1 is 5.4 meters per second. Do we care what direction that skater is going? No, because energy isn't a vector. Yay. Okay. Neglect. And we want to know the height h above the ramp. So if we call this position position 2 at this certain height above the ramp, then we want to know what the height of position 2 is. Okay, what's something that we know about that skater? We're assuming right at the skater's maximum height, just like with projectile problems, we're assuming that the speed at position 2 is 0 when they reach their highest height. Do we know how far the skater is above the ground at any point here? No. So it makes the most sense that this line that we're provided with, right, that kind of skims the top of the half pipe, this will be our height equals 0, right, our reference line. So that means at position 1, the skater has a height that is equal to 0, okay, because we're setting the top of the half pipe as our reference line. And that's okay, because we don't really care what the skater is doing in the half pipe. We also know that the motion of the skater, if we're neglecting friction and air resistance, the motion of the skater at position 1, right at the top of the half pipe on the left side, will be the same height that the skater, or is the same height that the skater is at the top of the half pipe on the right hand side, and that the skater will be going the same speed, right, when they launch themselves up like that. Okay, so let's compare energy at position 1 and energy at position 2. So at position 1, we just have kinetic energy, no potential. It's 1/2 mv at position 1 squared. At position 2, up here, there is no kinetic energy, so there's just potential energy, mgh at position 2. We can see then each term has a mass, conveniently, because we were not given the mass of the skater, and we get 1/2 5.4 squared equals 9.8 times height 2. All right. Okay, and we get that the height above our reference level that our skater was able to achieve is 1.5 meters. Okay, let's take a look at one more example. It's a little bit more complex, and it's a really good one to end with. All right, so our drawing shows a person who, starting from rest at the top of a cliff, swings down at the end of the rope, releases it, and falls into the water. There are 2 paths by which the person can enter the water. How fast is he moving when he releases the rope on path 2? Ignore the effects of air resistance. Okay. So we want to know how fast this person is going here when they release the rope at path 2. Right, so path 2 is right here, and we want to know what's going on right when they release at this position. So how fast is this person going? Right, we'll just make them a big dot, like right here. What do we know? What else do we know here? Oh, the other thing, we don't know the height of the cliff, right? We don't know an awful lot, right? We know that like at the top of the cliff, we can assume that this person is starting from rest when they step off of the cliff, that they swing down. What we do know is when the person lands in the water, if they release and follow our path 1 here, when they land in the water, they have a speed of 13 meters per second. And so this is an example of where the beginning of a object's motion isn't necessarily what we want to choose as our initial condition. Okay, we want to pick 2 positions in our object's motion that we know the most about, that we can compare. All right, so what we know is we should probably call this position 1 and this position 2, right? Because we know at position 1, when the person lands in the water, that they have a speed of 13 meters per second. We also can assume that the water is the reference level. So at position 1, there's a height of 0. We're looking for how fast this person is going at position 2, right before they let go of the rope swing. And we are given their height at that position as 5.2 meters. So let's set up a law of conservation of energy problem. Now that we've looked at, right, determined which 2 points in the person's motion we're going to compare that we know enough about, and now we can solve the problem, right? So at position 1, we just have, right, there's no gravitational potential energy, there's just kinetic. So we'll write at position 1, there's just kinetic energy. So there's just 1/2 mv at position 1 squared. At position 2, we've got gravitational potential energy, so mgh at position 2, and there's some kinetic energy, so 1/2 mv squared at position 2. We're ignoring the effects of air resistance, so we assume that there's not any work done by non-conservative forces. And that allows us to cancel out the mass of our person. Okay, let's plug in our values and see what we get. All right, there we have it. We plugged in our values that we were given at positions 1 and positions 2, and we got a value for the speed at position 2 of 8.2 meters per second. Now it's worthwhile to stop and consider if the value that we calculated makes sense. All right, we would expect the person to be going at the person to have a smaller speed at position 2 because they are up higher above the ground, right? Down at the bottom at position 1, there was the total energy was all kinetic energy. As that energy transforms into some gravitational potential energy, you lose kinetic energy, meaning your person is slowing down, and so we'd expect a smaller speed, right? And that's what we got, a smaller speed, because some of the energy was transformed into gravitational potential. Okay, so our value does make sense. All right. So here are some problems for you to consider. In your textbook, I've listed the sections that we've looked at over the last several days. So work energy theorem and the law of conservation of energy, ignoring friction and with friction. These are posted on Canvas. And so I'd like you to consider those. Some of these I have previously assigned. You may or may not have felt comfortable with the problem-solving process until now, and so it might be worth revisiting some of the problems that you may have struggled with from last class. Okay, remember there will be a check for understanding quiz on formative as part of your assignment on Monday's asynchronous class time, so please make sure that you're checking with me on office hours if you need any support with these problem-solving processes. All right, have a great day.